Hello students, welcome to the next section. I would like to introduce what are the examples of connected spaces. So in the last class I have proved that a theorem which are equivalent conditions of connectedness. So remember, when a topological space X2 is connected, we have connected, I can say that first one, X cannot be written some union of two sets A and B where A and B are non-empty open sets. Second one, when X is connected, I can say that cannot be written union of two sets A and B such that A and B are non-empty closed sets. And third one, when a space is connected, the only open sets are, means both closed and open sets. Open sets are the empty sets in the whole space. And fourth one, if you consider any proper subset of X, non-empty proper, X A not equal to empty, and it is when you consider any non-empty proper subset of X, it has non-empty boundary. Its boundary will be non-empty. So these are four equivalent conditions of connectedness. So using these conditions, I can say that when you consider an indiscrete topological space, I denote indiscrete topology as tau I, where tau I is indiscrete topology. That means tau I is nothing but only empty set and whole space. Okay. Then what are the open sets with respect to this topology? You know, these are the open sets. Its complements are closed sets. What are its complement? Closed sets are complements of these open sets. Complement of empty set is X. Complement of X is empty. So the open sets are empty and X. The closed sets are X and empty. Therefore, the open sets are both closed and open. It is both open and closed, empty set and X itself. So you get the only open sets in indiscrete topology is empties and X. So the third condition valid here. The only open sets are empties and X. Therefore, indiscrete topological space for any set together with indiscrete topological space is always connected. Okay. Another example, you consider X is equal to a singleton set A. Then you find out discrete topology on X. Discrete topology. Tau D equal to discrete topology on X. What will be the discrete topology? Subsets of X. So it is nothing but empty set and singleton A. That is nothing but empty set and the whole X itself. So when you find out the discrete topology on a singleton set, which is nothing but indiscrete topology. Okay, it is nothing but indiscrete topology on X. So discrete topology on a singleton set, singleton is indiscrete topology, same as indiscrete topology. So I can say that any one element set together with discrete topology will be connected. Therefore, I can say that singleton with discrete topology is connected. Okay. So what about the case of a set having more than one element with the discrete topology? So if you consider, let X be any set, with cardinality greater than 1, okay. Then consider the discrete topology on X and consider discrete topology on X. Okay. Can you say that it is connected? And you know, in discrete topology, all the subsets will be open and all the subsets will be closed also, because if we take x is equal to 1, 2 as a set, then what will be discrete topology? It is empty set, singleton 1, singleton 2 and x itself. So these are the open sets here. And what are the closed sets? Closed sets are its complement. What are the closed? Empty complement is x, 1 complement is 2 and 2 complement is 1 and x complement is empty. It is same as this. So in discrete topology, all the subsets of x will be both open and closed. Therefore, all the subsets are both open and closed. That means they are closed. That means they are open sets. So in discrete topology, if the set has more than one element, then every proper subsets are also open sets. Therefore, I can say that discrete topology will not be connected if it contains more than one element. Because when a space is connected, the only open sets are empties and x only. When you consider the discrete topology on finite sets or infinite sets, every subset will be open. Therefore, it cannot be connected. Therefore, all the subsets are open. Therefore, it is disconnected. So that I can say that the only connected discrete spaces are those which consists of at most one point. രണ്ടിൽ കൂടുതൽ എലമെൻറ്റ്സ് വന്നു കഴിഞ്ഞാൽ, അതായത് രണ്ടിൽ കൂടുതൽ എലമെൻറ്റ്സോ വന്നു കഴിഞ്ഞാൽ തീർച്ചയായിട്ടും ആ സ്പേസിൽ ഓപ്പൺ സബ്സെറ്റ്സ് ആയിട്ട് 5ഉം എക്സും മാത്രമല്ല ഉണ്ടാവുക. അതുകൊണ്ട് അത് എന്തായി മാറും? ഡിസ്കണക്റ്റഡായി മാറും. അപ്പോൾ ഡിസ്ക്രീറ്റ് സ്പേസുകൾ കണക്റ്റഡ് ആവണമെങ്കിൽ മാക്സിമം അതിൽ 1 എലമെൻറ്റേ ഉണ്ടാവാൻ പാടുള്ളൂ. ഓക്കെ. നൗ ഇപ്പോൾ ഇൻഡിസ്ക്രീറ്റ് സ്പേസ് അല്ലാതെ വേറെ ഏതാണ് കണക്റ്റഡ് ആയിട്ടുള്ള സ്പേസുകൾക്ക് എക്സാമ്പിൾ ആവുന്നത്? സോ യു ക്യാൻ സേ ദാറ്റ് Sierpinski space which are always connected, because the only open sets are empty sets, and since the only open sets are empty and capital X only. Okay, now we are considering examples of disconnected spaces. For that, I consider the subset of Q of real line. So since real line with the usual topology is a topological space, Q with the subspace topology, that means tau u restricted to Q, is a topological space, which is a subspace of R with tau u, topological space, where tau u denotes usual topology or standard topology. Okay. What about this topological space? Is it connected or disconnected? So if it is connected, it cannot be written as disjoint union of two open sets or two closed sets, or any other properties of connectedness must satisfy, right? So I consider here, take A equal to set of all x in Q such that x less than some alpha, where alpha is any positive real number, okay? And B equal to set of all x in Q such that x is greater than alpha, where alpha is any greater than any real number. Okay. So when you consider this alpha as an irrational number, where alpha belongs to R and alpha is irrational, okay, R minus Q. Alpha belongs to R minus Q means alpha is irrational. Okay. So what will be A and B? Is it open or closed sets? So I can say that what is this? When you consider some alpha as irrational number, then A is nothing but set of all rational numbers less than alpha. Set of all rational numbers belongs to this area, this region. Okay. What is B? B is nothing but set of all rational numbers belongs to this region. So this will be A and this will be B. So I can say that what is A? A is nothing but when you consider minus infinity comma alpha, instead of alpha I can write some A. Okay, A. So minus infinity A intersection Q. That means you consider set of all real numbers which are less than A. Then you take rationals. So this A is nothing but minus infinity to A intersection Q. അല്ലേ, ഈ ഏരിയയിൽ നിന്നും റാഷണൽസ് മാത്രം എടുത്തതാണ് എ. ഈ ഏരിയയിൽ നിന്നും റാഷണൽസ് എടുക്കുക പറഞ്ഞാൽ വാട്ട് ഈസ് ദിസ് ഏരിയ? ഇറ്റ് ഈസ് നത്തിങ് ബട്ട് ദിസ് റീജിയൻ ഇസ് നത്തിങ് ബട്ട് minus infinity to A interval, open interval. We are omitting this element, so therefore it is nothing, an open interval minus infinity to A. Then you pick out all the rationals from here. So it is nothing but A is minus infinity A intersection Q. Okay. What is this set? Open interval minus infinity comma A, which is an open set, which is clearly an open set in real line with the usual topology. So minus infinity comma A is open in real line with the usual topology. So when you have an open set in real line with the usual topology, which is intersection with the Q, will be an open set in the subspace topology of Q. Therefore, A is open in the subspace topology of Q. Okay. And it is non-empty also. And A is non-empty also, clearly. What about B? B can be written A comma infinity intersection Q. Right? You consider this area. This area is open interval A comma infinity. Then you pick out all the rational elements in this region. So that is nothing but B can be written interval A infinity intersection Q. And this is nothing but an open set in real line, open in R. Therefore, B will be open in Q and B is non-empty. Okay, so all the rationals in the real line can be written rational, because since A is irrational, A cannot be belongs to Q. A cannot be belongs to Q. Then you consider all the elements left of A which are belongs to rationals and all the elements right of A which are belongs to rational, right? So Q can be written set of all x in A union set of all x in B, right? അല്ലേ, ഇവിടെയുള്ള മൊത്തം റാഷണൽസും ഇവിടെയുള്ള മൊത്തം റാഷണൽസ് എടുത്തു കഴിഞ്ഞാൽ ടോട്ടൽ റാഷണൽസ് നമുക്ക് കിട്ടും. എ ഇറാഷണൽ ആണ്, എ അതിൽ ഉൾപ്പെടുന്നതേ ഇല്ല. സോ ദിസ് ഈസ് നത്തിങ് ബട്ട് എ യൂണിയൻ ബി. സോ വാട്ട് ഈസ് എ? an open set of Q. What is B? An open set of Q. And you know that A and B are non-empty. Also, what is A intersection B? A intersection B is minus infinity A intersection Q intersection minus infinity, A comma infinity intersection Q, and this is equal to minus infinity A intersection A comma infinity intersection Q, right? This will be A intersection B. And what is this? This is always empty. So empty intersection Q, which is equal to empty. So A and B are disjoint. കാരണം ഇപ്പുറമാണ് എ ആണ് അതിനെ നമ്മൾ സെപ്പറേറ്റ് ചെയ്യുന്ന എലമെൻറ്റ്. സോ തീർച്ചയായിട്ടും ഇവിടെയും നമ്മൾ ഇൻ്റർസെക്ഷൻ എന്തായിരിക്കും? empty ആയിരിക്കും, because they are disjoint. So that Q can be written some A union B where A and B are non-empty sets and their intersection is empty means Q can be written disjoint union of two non-empty open subsets. So which means Q is disconnected. So rationals with usual topology is a disconnected space. Okay, which is a disconnected space because it can be written disjoint union of two non-empty open sets A and B, which are of the form like this. So that the subset Q of R is not connected. Then what are the subsets of R which are connected? Q is not connected. So you can prove that any form of interval will be connected subset of R. So the connected subsets of R, the connected subsets of R are intervals. So real line with the usual topology is always connected also, because R is nothing but interval minus infinity comma infinity. Okay. Now I recall what is the definition of separated sets. Two sets A and B are separated means if A closure intersection B equal to empty and A intersection B closure is equal to empty. What is a disjoint set? Two sets are disjoint means their intersection is empty. Okay. Then I can prove that A comma B are separated if and only if A and B are disjoint closed sets in A union B. So when two sets are separated if and only when A and B are not disjoint, which are disjoint closed sets in A union B. മനസ്സിലാക്കണം, separated ആണെങ്കിൽ disjoint ആണെന്ന് നമുക്കറിയാം. When A and B are separated, that will be disjoint. The converse may not be true. But the converse is true when these two sets are not only disjoint but also closed sets in A union B. How will you prove this? Suppose A and B are separated. Then by definition, A closure intersection B equal to empty and A intersection B closure equal to empty. Okay. Now you consider A intersection B. What is A intersection B? A intersection B will be contained in A closure intersection B, because A is contained in A closure, B is contained in B. Okay, so A intersection B is contained in A closure intersection B. What is this? A closure intersection B equal to empty, right? So I can say that A and B are disjoint. Now we have to prove that A and B are closed in A union B. A comma B are closed in A union B. That is, when you consider A closure with respect to A union B, that is equal to A, and B closure with respect to A union B, that is equal to B. This is you need to prove. So for that, consider what will be A closure with respect to A union B. A closure with respect to A union B is nothing but you consider A union B intersection A closure. So it is nothing but A intersection A closure union B intersection A closure. So what is A intersection A closure? You know, intersection between two elements is nothing but when one is contained in another, the smallest one will be their intersection. You know, A will be always contained in A closure. So what is A intersection A closure? It is A. So A intersection A closure is equal to A. What is B intersection A closure? Since A and B are separated, B intersection A closure, yes, B intersection A closure is empty. So A union empty equal to A. So which implies A is closed in A union B. Okay. Similarly, what is B closure with respect to A union B? It is A union B intersection B closure. So which is equal to A intersection B closure union B intersection B closure, which is equal to, this is empty because they are separated, empty union B, that is B. So you get B closure with respect to A union B equal to B. So which implies B is closed in A union B. Now for the converse part, conversely assume A and B are disjoint closed sets in A union B. How will you prove they are separated? They are separated. To prove they are separated, we need to find out A closure intersection B and A intersection B closure, right? Since they are disjoint, which implies A intersection B will be empty, right? Okay. And you can say that what is A intersection B? A intersection B is always contained in A closure intersection B. And since A is closed in A union B, I can write A closure intersection B is contained in A intersection B. So which means since it is empty set, A closure intersection B will be empty. Similarly, I can prove that A intersection B closure is also empty. Therefore, A and B are separated. So when two sets A and B are separated, then which is if and only when A and B are disjoint closed sets A union B. Okay. Now we will prove a theorem. Theorem says that suppose X be a topological space. Okay. Suppose X be a topological space and C be a connected subset of X. Then we have C, which is connected subset, which is connected. Okay. Suppose C is contained in some A union B, and this is A union B. Suppose C is contained in A union B, where A and B are this, it is nothing but some, suppose like this. This is A and this is B. Okay. Suppose C is contained in A union B and A and B are mutually separated subsets. A and B are mutually separated subsets. Then either C must be contained in A or C must be contained in B. In this picture, I have drawn that C is contained in A. Okay. This is we need to prove. Okay. This is very important also. How can you prove this theorem? For that, for proving this, I'll take let G equal to C intersection A. Okay, and H is equal to C intersection B. Since C is a connected subset of X, you consider C comma tau restricted to C, which is a subset of, which is a subspace of X tau. Okay. Then how can you define a closed set in the subspace topology of C? So a set is closed. Suppose a set P is closed in C means P can be written some C intersection Q where Q is closed in X tau. Okay. So a set is closed in the subspace topology if it can be written C intersection Q where Q is a closed set in X. Okay. So I can say that here G and H are closed sets of C. If I say like this, A and B must be closed sets. So you know, since A and B are mutually separated. So when A and B are mutually separated, then by previous result or previous problem I can say that then A and B are disjoint closed sets in A union B. So when A and B are closed sets in A union B, what about C intersection A and C intersection B? A is closed. When A is closed, C intersection A will be closed set in C. Since B is closed, C intersection B is closed set in C. Okay. Which implies G and H are closed sets in C. Connected set C. Okay. Then what is G intersection H? G intersection H is equal to C intersection A intersection C intersection B, which can be written C intersection A intersection B. Since A and B are disjoint, C intersection empty, and which is equal to empty. Okay. And what is G union H? G union H is equal to C intersection A union C intersection B, and which is equal to C intersection A union B. What is C intersection A union B? C is contained in A union B. So C intersection A union B is C. Since C is contained in A union B. So what do you get now? G and H are two closed sets in C, and their intersection is empty, and their union equal to C. Which means C equal to G union H, and where G and H are non-empty disjoint closed sets in C, which implies C is disconnected. Is it possible? No, because C is a connected subset, right? So which is not possible. That means when C is contained in A union B, we can prove like this. So that means C cannot be contained in A union B, or if C is contained in A union B, C must be contained in either A or in B. Which implies since C is connected, C must be contained in A or C must be contained in B. C cannot be contained in A union B. So the theorem says that when a connected subset is contained in union of two sets, and that two sets are mutually separated, then that connected set must be contained in any one of them, fully contained in any one of them. Okay.